Section 4.4 deals with linear combination and span. Linear combination and span. So a linear combination is just adding a scalar of one vector to another vector. So if we have vector 1, vector 2, vector 3, an example of a linear combination would be twice vector 1 plus 3 times vector 2 minus 4 times vector 3, whatever vector 1, 2, and 3 are. So as long as we are just adding vectors multiplied by scalars, that's a linear combination. If you think about an equation like x plus 2y equals 4, that's a linear equation because we don't have any exponents. We don't have a variable times another variable or a variable times itself. At most, we might have a constant times a variable, constant times another variable added together. So linear combinations go beyond just a line. We can have a linear combination of lots of things. A linear combination of matrices. If we have this matrix and this matrix, a linear combination could be just adding those matrices together. It could be doing twice one matrix plus 3 times the other matrix. It could be adding twice one plus -3 times the other. So as long as we're at most doing a scalar times one and a scalar times the other and adding them together, that's considered a linear combination. So I want to define a span. I'll just read their definition to start with. The vectors v1, v2, v3 through v sub n, which are vectors in a vector space V, so V is a vector space, they're said to span V if every vector in V can be attained, well they say can be written, I'll say can be attained from a linear combination of these vectors. So a set of vectors is said to span a space if we can attain every possible vector in that space using some linear combination of those vectors. Give you an example of that. Let's look at the space R2. We can write any vector in R2 as some I hat plus some j hat. Or we could call that A plus that, B, where this is the horizontal component, this is the vertical component. If we call that x and y, then we can attain any vector with some combination of I hat and j hat. If I want the vector, or the vector 7, 5, let's write it this way, 7, 5, then that would be 7 I hats, 5 j hats. If I want the vector -4, 6, then that's -4 I hat, 6 j hats. So you could say that I and j hat span R2. we can get any vector in R2 using a linear combination of I and j. The same thing is said for R3 using I hat, j hat, and k hat. K hat is just the unit vector in the z direction. Sorry, I have a 2-year-old that needs a snack. Just 1 minute. Now that we've defined what span is, let's look at an example and let's try to see um, whether or not the two given vectors, whether they span V. So we're going to say that V is R2, and let's see if these two vectors span R2. So in order for these two vectors to span R2, if we take a combination, let's say A1 times the first one plus A2 times the second one, we must be able to get any vector in R2. If we can't get any vector, then these two do not span R2. So if we multiply this out, we look at the top equation. If we think about it as two equations, or we'll just multiply it out to start with. We got A1, 3A2, 2A2 equal x, y. This is just an arbitrary vector in R2. So A1 plus 3A2 be x. A1 plus 2A2 would equal y. So let's write this as an augmented matrix. And let's try to see if there is a way to relate A1 and A2 to any vector x and y. So let's row reduce this. Let's let the second row be the opposite of the first one plus the second one. So if we do that, the first one stays the same. We get a 0. The opposite of this plus that is -1. The opposite of this plus that is y minus x. We can get a 1 here if we want to. Just on the second one, multiply through by a negative. So if we wanted to, we could get a 0 here. So let's let our new row 1. To get a 0 here, we would want this to be -3. So -3 R2 plus R1. So the bottom row stays the same. The top one, 0 plus 1, -3 plus 3. Do -3 times this one, this would be -3x. And a plus 1x would be -2x. -3 or -3 times -y would be positive 3y's. No more y's. So basically what we have here is that A1 is minus 2x plus 3y. A2 is x minus y. So if you give me a vector in R2, then I can tell you what A1 and A2 would have to be. And remember that A1 is just the scalar that's multiplied times the first. A2 is the vector multiplied times the second. So if you tell me what vector you're trying to get, I can tell you what we need to multiply each of the vectors given in the subset by, or in the span, to attain that given vector. For example, if we want to get 5, 7, then A1 is negative 2 times 5 plus 3 times 7. So A1 is 11. A2 is 5 minus 7, or negative 2. So let's see if that really works. Let's take this and we'll bring it down to the bottom. So if we replace A1 with 11 and A2 with negative 2, we get 11, 11 plus negative 6, negative 4, which gives us 5, 7. And since we have a relationship between x, y, a1, and a2, we can achieve any vector in R2. So if we can show that this exists, which basically if we set up our augmented matrix, row reduce it, and we find out that there is a solution to that, then that shows that, yes, those vectors do span that particular space. Now briefly, let's just mention, well, when do we have two vectors that don't span a particular space? If we row reduce and we get something like this, then there's no solution to this. Looking at this last statement, unless the the vector space that we're trying to look for is a vector space that always has a 0 in the y component, then this says, hey, there's no solution to that. So we have to be careful there. Also, one of the theorems, or something that you may read in here, is that if we have a set of vectors, if these vectors span V, then if we were to come in and add another vector with them, then that will also span V, which makes sense. If those by themselves span V, then having another vector with it is not going to make it not span. If you think about it, if we do something times the first one, something times the second one, something times the third one, if those span V, then I mean, we can let D be 0, and we still just have a V1, V2, V3, which span V. So if we know that a certain set span a subspace or a vector space, we can add as many more additional vectors to that as we want and not shrink our vector space, or not unspan it.